So in the last lecture we have been working on our implementation here, and we had the problem that we didn't manage to send any messages back. I have reviewed the code again. The found the issue. We have been clearing here the message header, which is wrong. We need to keep it so that the ALPC mechanism knows where to route the reply, which we are assembling here back. When we remove this and run the thing, we also have a few log lines. Start client, start server, start client. Then here we can see on the log lines that we get the reply. We can also, of course, put a breakpoint into our client side receive function, this one, and see that we will successfully receive a reply from the server now with this small fix. Do we not client, there seems to be some other small issue. Let's put the breakpoint a bit closer to what we want to do. So LPC socket. Alright, I think that there was a second issue that we don't finish this receive loop here. Let's put the breakpoint, for example, here. So we server, we client, and then get up here. Now we got a reply, so we have status success, and then we will be able to read. So it also tells us that we get 16 bytes in the reply. Then read the reply into our buffer, which now should contain some data. And what other issue we run into is that we never finish this receive loop, so this will need to be improved as well, because we are like total receive is 16 and that should be all. But we never break out of this, and this can also be of course fixed, but the question is whether we want to proceed on this route or whether we want to improve our mechanism. So generally the use of this request reply mechanism here seems a bit inefficient, in the sense that the client is basically pulling for replies. So if the server sends something out of order, we will not get this unless we check what's happening here. So first things we will do is we will quickly fix here the mechanism so that we once we get a reply that we exit off this loop and then really proceed with the rest of the operation. So we put a breakpoint here now. It needs to start port client, and when we arrive here at some point we'll get response. So we should get a reply. I think so it was still 0. Now let's just put the breakpoint here. At some point we will go through this thing. Just pulling data. Although it might be that sometimes we still have a synchronization issue. Let's just restart this once more. Right, so we arrive here and we know how long the package is that we received, and what we need to do now is we need to read the reply header. So we are receiving not just a normal empty block, but what we are getting is here this message, less data. We take a look in this memory that we have received there. We can close this. We have here some header which is 8 byte long, and then we have our actual text. And when we go back to our server, that's not the right one, server here, we see how this is formatted. So we operate with this where is it, fourth message header, this one, which, as we might remember, should have a total size of 8 bytes, since there is some padding here involved. So what we now need to do is just format this. So we stop this for now, go to our socket, and here, once we have received something, what we'll do is we'll make a new variable to receive, which will indicate how much data we actually are expecting. We have here our res data, and then we just check if this, we need to initialize this, we had with 0, so if this is null, then it means it's the first package in a line of packages. So if this is null, then we will initialize it with the value from the header. Header, we had here total size. And for now, let's leave it this. Let's see how the code behaves. So what we want do ultimately is just to compare the amount of received data with this value. And then we see 8, since the first 8 are not relevant, so we only count the payload itself, the reply text. And this, of course, here, total receive, we should also slightly introduce a new helper value somewhere, because here we are directly at the res data place. What we actually don't want, we want to only put into our buffer the data which we have received, not counting the header. So we need to shift this slightly. So let's char asterisk parent data is equals res data. This should be defined as uchar. So let's stick to this. Plus size of port header. And then, of course, we need some length. Len is equals data length minus size of port header. Oops. Right. So we have our data, which we then attach as char here, and as length we take our truncated length. For the total received, we should go with this len here as well. Then we can unlock and do the next loop, or we just check. So if so what we can do is we can subtract what we have received from what still is to be received, and if this is null, then we break out. So if this is null, then we break. Yeah, when we unlock is not so important. Let's do it here. Okay, let's run it again. Server, let's put a breakpoint here before we start the client. So we break out, then we can inspect our helper buffer. And it contains the expected text. When we continue, I think what we're still missing is to invoke a signal that there is something to be actually read. So we can go back to our socket. Signals. Signals ready read. We need to trigger this. And then break. Okay. Client. And now we are finally arriving here in our on-client data function, which handles the data received from the server. But as I mentioned earlier, this design here, while currently working, is not quite ideal. We had quite a few hacks that we wouldn't want to have in production code. Like, for example, here somewhere we wait until the server replies something, but we don't really know how much the server will reply, and if this all happens asynchronously, we might run into issues. So I have revised the implementation a little bit, and now we will a bit faster try to just go through the new implementation and and make it work. So we will first start with modifying how the server works, and then we will update the socket, so more functionality have been moved into the socket. In our previous design, the server had quite a few things to do. Now almost everything will be done by the client socket. So port server, and yeah, we don't need to change any header files on the server side. We can remove a few things which we will not be using here. So the in use, or just completely move them. This can go away. We just keep the most important information. Then what we also can improve is the way how we handle this connection. We can here set a object context, pod context. So we just use the pointer to our current client object. This value can be then retrieved whenever we receive a package, and then we know for which communication channel this was in fact relevant. Right, then we will need to change this, but we will do that slightly later. So this just make it mark it with to do. I'll try to keep the changes in somewhat logical order, so not just changing things willy-nilly everywhere, and then you need to read the whole code to understand, but I'll try to at least at some point go step by step. Right. So here we can remove a really large code section, starting from here until pod disconnect. So this functionality, processing the requests and replying, will be moved to the socket. So this will simplify a few things. Okay, so here we are inside our thread function, and the most important change is that we will no longer use this mechanism where we call a function which will send a reply and wait to receive the next request. Instead, we'll be only using instant requests which do not wait for a reply, and in turn they can be sent from each side independently, which mirrors how a normal pipe mechanism or general normal socket mechanism works much closer than what we are doing here. So we'll be removing those two variables as well as the space for it. So since now we will be only handling the incoming messages here. This can go away as well. We still want to mem set the header of the new message. The logs we can leave, and this thing here I will be using m server, and the reply message is always null. But as I mentioned, we have the ability to get the pod context, so we can do that. Void pod context equals null. This will be the value that we have saved before into the here. We'll get this pointer back as pod context for every communication after we of course have accepted the message. So before the message got sorry, the communication was accepted, there will be no context. So like some of the messages that we have here will just give us a null context, but the relevant ones will give us the value that we want to see. Okay, so of course the replay part here goes away, since this simplifies a lot of things. Okay, this also goes away. So there are different types of messages. We can get this request reply. This is what we were using before, but there's also this type datagram, which basically means it's a one-way message. One side pushes it, the other side receives it, and that's the end of the communication. Of course, the other side can at any point in time send an own datagram, and the behavior is what we want. The other messages are for managing the actual connections, so those will still stay. So we change the whole content here, or at least a portion of it, to this datagram. Right, so the type, we need to change the datagram. Then we want to get the socket and the helper. The rest here can go away. And then we just check and right, one more thing. We have here find pod client based on message. That should be that could be fine. For now we can leave it. We could improve this later on with the pod context. But let's go step by step so that we have something working, and then we can see on the further improvements. So if msg u1 s1 data length. So if this is not 0, then on our helper, have it here. On our helper, we read datacam, which we don't have yet. That will be a function we need to add. So for now we leave it. Let's call just the read data. Alright, and then of course we still have here the disconnect, which we have not yet handled. So this might need also to be implemented. But for now, I said we want just to get this to operate. So for the server side, this is already all the needed changes. So it wasn't that much. Most changes will be on the socket side. Socket. So let's see. So one thing we will change is we will just drop this port header, since we will not be differentiating between follow-up messages and the initial message. We just send datagrams with the data as they come in, given that our communication paradigm is really just using a data stream where we just push in data. The packaging is something that needs to be done by the calling applications, and not again done here on the lower layer. So this we can completely remove for now, and then we will improve our helper. So we need to add a few constructors. The destructor we actually I don't think we need it, but we need the constructor, this normal one we need, and then we need a second one. Void asterisk pack and port and 32 max message length. This thing will be calculated. Now we can quickly take a small detour back to our server, because as you might remember, we have not done this here. So now on this side we can make the change that we have been omitting before. Just add here the pair client port and max port msg len max port message length, so that we have here this information available. So on the client side, we receive the port length from the connect function, but on the server side, we know that we are the side that defines it. So we just use our preprocessor define, which we also then, when creating the port, are feeding here into this create port. Also, I will remove this part of the code, since we won't be using the more advanced features. Let's just keep it concise. Okay, so let's return to our socket header and see what else we need to change. So we added a new constructor, which we need to add in the body. Then we will need a few more functions. We won't need a q64 write data, const char asterisk data, comma q in 64 len. And we also need a void read data, which just looks quite, which takes the message from before. So this is the function we have not yet implemented on the other side. And since we don't have the definitions available in this scope, we can use a trick. We just need to tell the thing that it is a struct, and that its name is port message, and that when we are using a pointer, this is all the compiler needs to know. It doesn't need to know any internal fields of this thing, and this is how this nice trick works. Since we added this here, should have no more we have a typo. We need to one more thing. So the function is now there, but it's not accessible. We need to add here a few definitions. Friend on segment long. The nice thing about this protected mechanism is that we can also define individual functions as friends, so that they can access the protected members. Unless I have a typo, it should be fine now. And now it took it. Message. Do I have a typo somewhere else? Oh, message. That should be correct. Message asterisk. We will see what it complains about when we try to compile it. Now it's not complaining anymore, so it was just not up to date. Good. So we have our read function, write function. We will implement an own. We'll move the this thingy to the helper, since it will need to be able to access this thing. So we need to add a few more friend functions here. So we have this, we have this. We can remove the send buffer because we will be sending everything instantly. We will not be delaying, so this replying function goes away as well. And we will add a destructor which is public, which we have not added here before. Destructor public. Okay. Then here, what we have forgotten to add, what we will add it now, just for completeness, will be a close function. So close is already defined on the QIO device, but we want to have it here so that we can properly terminate the communication. This goes away, and this goes away as well. And I think the header should be fine. So let's proceed with our internal implementation. So we'll add here an additional variable, handle hack client thread. Since we have now a reading thread, then we need to have it here as well. Then our helper has got quite a bit more complicated, so it needs two constructors and a destructor. Socket here, this one. Zack. Okay, so the normal constructor is quite trivial. It just makes m is equals new this thingy. The other one's a bit more sophisticated. It also will set a few things. Is aside will now be done here. Max data len we have here as an argument, and client port is equals handle client port. Okay, and actually we don't need a new line here, and the destructor will just delete m. That's some space. And now to the more useful functions. Those two, the write data and read data, that do all the job. So Zack. Okay. Let's first do the read function and do the write function. So q lock lock. We still need to, of course, lock the buffer here when we are writing to it. You char msg data is equals uchar msg plus the size of port message, then ulong msg len is equals msg u1 s1 data length, right? So okay, just with receive buffer punkt append char msg data msg len close, yeah, lock unlock, and if we actually received something, I mean it might have been a message with 0 length. I mean we could have checked earlier, but well, we emit ready read, and as you might remember, ready read is a signal we have here, which is then connected to another signal on the parent object. So this works quite nicely to relay those communication. Yeah, so which then brings us to our other function, our write function. So the write function is something we need on the server side as well. I think we forgot to add that. We will see. No, maybe not. Actually, we'll just call it directly from the socket, so it really doesn't need to be on the server side. The server side really will only be here for the receiving of the data. Okay, so qint64 send total 0 uchar, let's call it just buffer max port msglen, so we always assume it as big as possible, port message asterisk header is equals port message buffer uchar data is equals request buffer plus m size of port message. Okay, then while we have something to send, len write more explicit is greater 0, and once we are done, of course, will be returning the total size. Let's do it now before we forget it, and inside our main function, oops, wrong, send len, or let's call it to send maybe, oops, to send. That will be the length of the data that we can send in one message. We check if len is greater than max data len. If it is, then we stick to just this much, else we take length as we got it. Now we clear the header, comma 0, comma I copied it already, nice. Port message header size, header 1 s1 first data length is equals to send, and then total length is equals to send plus size of port message. Actually, let's do it like this. Okay, then we set the data memcp data comma data comma, so the data with the capital D is our buffer plus something, while the other data is what we actually want to send. Small s, and then we advance our data pointer plus equals to send, and len gets decremented by to send, and enter status is equals enter. So the nt request port function just sends a datagram package without waiting for a reply or something like that. Client port header, and if this was failed, so if exclamation mark nt success, so if this failed, then we do two things. So if send total is 0, then we set this to -1, so that we return an error, and we break in any case, and that makes me think we should have this here, so that if we would retry, that it would work out instead of us losing some data, and this thing gets plus equals, of course, to send. Okay, yeah, so that should be this part done. It will be just sending as many packages until the whole thing we wanted to send has been sent, so it's quite straightforward. It does not respect any buffers or unacknowledged messages or anything, but given that we want here rather a fast communication, we will not be implementing such additional things. Right, so here we can of course remove m, since we have helper that does all that. Then we added a close function from here, so we will need to implement it. This can also go away, we don't have m. And helper is held by a smart pointer, so we don't need to clear it explicitly. Right, so handle handle is equals interlocked exchange pointer. We won't just atomically swap the value in our m per helper m client port to null, and we use this function, and this function returns us the previous value, so it's quite nice. Now if we had the port, then we just close it. And the other thing, of course, we need to check if there's a thread. That was this here. Client thread. Then we just wait for it to terminate. Wait for single object. Thread of infinite. That brings me to something we might have missed. Okay, now we have this here. We need to add somewhere some code to terminate the thread reliably. Oh no, the thread will terminate itself automatically, because what we do is here we set this to null, and when we look on our thread, which is not yet implemented, which we'll implement soon, we will see that there will be a in the loop it will be checking whether this still exists, and if it does not, then it just terminates itself. So basically doing this line already tells the thread to end itself. We here only need to wait for the thread to have finished whatever it was doing. Right, so let's steal some lines of code so that we can type less from our server. This is just called port socket. And here we also, of course, need to update this name as well. Yeah, so enter status, need some status variable, future space. We are in principle copying a bit what we have done on the server side. Max port msglen port message asterisk ms k equals port message space. It's pretty much the same code we had here. We don't have any context because we are on the client side, so we only communicate with one other party from this object. For now, our loop, not quite endless in nature. Right, and now we will status is equals enter, and enter, apply, wait, reply, wait, receive, but we will not set all the fields, so it will be just receiving the datagram and nothing else. Per helper, we need the helper. Oops, forgot to add a line here. So we grab the type of our helper. Per helper is equals oops, this thingy here. So we have our helper m client port null comma not received message is msg. Let's just copy a bit of the logging logic from here. This is of course now the client side. Okay, outside the client. CLI is like command line interface. The client is already chart is okay. Then of course we check whether this thing still exists. That's the place where we would bug out. If not this, then break. Client closing. Okay, and if enter, if not enter success status. Sorry, wait. Less typos status. Then we just break. We need to do handle error. We could of course try to maybe retry, but usually if we run into an error here, it's probably unrecoverable. And of course now we just check msg u2 s2 type is equals lpc datagram, and then helper read data msg. Oops. Okay, and we need to return something because the function expects it. Good. So here we have helper m. Here the same thing, and here the same thing. So we need a few things to be adapted. Here and there and there. This goes away. That one. Yeah. But what we need to this also needs to change and more changes. But what we also of course need to do is we need to create a thread. So one id helper client thread is equals create thread null 0, then our function, this one thread function, comma, that will then take the helper helper data. This pointer goes to the thread, and 0 and the reference on the thread ID, which we are not using. We forgot something. Here is a bug. We need to close that. enter, close, small l, and just for good measure, let's set it to null. This here was already set to null. Good. Right, so we have created our thread, which will be running and receiving communication. Now the server disconnect here will also need the same treatment. Oops. The important thing is the close here. This is what will, well, close everything. Okay. Now our write function will be completely different. We will just helper write data comma len, and we're gonna actually return this since we get nice error code if something fails. This can go away, this can go away, this can go away. Yeah, that might be working. Let's try it out. So as you see, the code is a little bit more cleaner also. Okay, we have a few mistakes. This says we already have a body. Yeah, probably. Oops. Yeah, here. This needs to go. Oops. Suck. And this is not relevant. And this. And why doesn't this like this? This should be working. There is a typo. It's just interlocked exchange. We're not comparing with anything. Okay, so start server, start client, and voila, we got our reply instantly. So it worked quite nice. We see here also in the log, we have the connection establishment, we have the incoming request, and here the reply, and that's already everything our application does. It doesn't do much more. So we managed to implement this now successfully, and I think more elegantly than what we tried before. This generally using this request reply mechanism is not bad, but on in the practical side of things, the downside of this is that it really kind of is very transactional, which is not suitable for all the types of communications. For the use for remote procedure calls, it's kind of ideal, because usually when you are calling a function, you want to get some reply, you want to get a return value, you don't want to just wait and get some reply randomly. But for a more generalized communication pattern, one where we want to be able to have this as a more or less drop-in replacement to pipes or sockets, there it is not quite ideal, and using here these datagrams as luckily offered by this mechanism is quite a significant improvement. There is of course one major limitation we will be always running into. This is that this is only limited to, I think this value is not this should be twice as much, but that does not matter. The important thing is we could of course change this to this ALPC version, which supports up to 64K message size, but this is also not quite so trivial, since this requires changing everything we are doing using all other functions, and complicates a few things. So for here we will leave it as is, but generally switching to ALPC the advanced version would also be, of course, a somewhat viable solution if one wants to do that. Are there any questions? Okay. Well, if there are no questions, then let's continue. So on our server side, we have not yet handled the disconnection in any meaningful way. Also, we have here still the old mechanism where we are identifying incoming requests by their thread and process ID, which is not ideal since we might in principle send data from different threads. So here, and send data from different threads into one socket, and then of course the other end would be confused if it receives a request from something that comes from a different thread. So what we will be doing here to improve on this is that we change this to this pod contexts, which we have already implemented but not used. So the idea is, just to recapitulate, that here when we accept the connection, we are giving the Windows kernel a pointer, basically a 8-bit value, which it can then which it remembers, and it will, whenever we then are receiving a message which is not of type connection or which is not of type connection, here it will populate this port context with exactly this value. This will happen for all the messages which for which it makes sense, so everything that is related to an existing somehow in process communication. So our datagram as well as the port disconnected, port closed, will receive such notifications. So we'll change this here, that we pass this data to our two functions. We will of course need to wait, the read doesn't need that, sorry, that was wrong. This needs it and that needs it here, the find function. Right, so this of course quite trivial. We just say void asterisk port context, and with the find function it's not so trivial because we need to change it, port context, and we will in fact change how we store our data, because our client's variable here will get a void asterisk instead of a handle, and then of course it means that here when we are where is that? No, sorry, we actually need to change a bit more. Because we have here, no, that's all we need to change. Define clients, yeah. So this will here pod connect. We will not be trying to re-find the one client. We'll always create a new client. Let's leave the other line in. We can set those data, it's fine, but here we will then, this we will set later. Oops. No, we can actually set it already here. We are just basically using our port context value, so our pay client here as a pointer. What you will notice here is that we kind of have twice the same pointer, once as a smart pointer of the right type and once as just a raw void pointer. And this in fact is quite useful, because the smart pointer as such, we need it so that it holds on to our client pointer, while we want somehow to be able to look up in the map, and usually smart pointers are implemented such that they don't cast to normal pointers, so we cannot use them as a key in a map. So here what you're doing is just you are using the same value as the key, and then when we get the context, we can try to retrieve something from the map, and if we get something, then we know it's valid, the smart pointer was still there and keeping hold to our object, and if we don't get anything from the map, then it means that the thing was removed, and at this point this is no longer valid. So port server. Right, so we set this here, client, okay. This is fine. This we want to change. So here we are now just always searching port context, and the rest does not change. And with the disconnect, it's somewhat similar, just that if we find something, we just erase it from the map. Erase F, and at this point it's gone. Okay, so this is also improved. Let's see what else we might want to change. So we of course have left quite a few to-dos, like for example our server is not not being shut down properly. That we could add here as well. we also should have a number of threads, so how many threads we want to start, although I think here we are already starting like whatever we specify, so we don't need to set this number. This would be just rather a bit boring. The destructor should first, of course, invoke close, and with the close we can we have one server object, so we'll just copy the approach from our socket close here. We just slightly bit more convoluted. So port handle, and this thing is now has what do we have this? We have this one server port. So we just set this to null, and we have here servers closing, so we already have the right code to handle it. So we close it, and then we need to wait for not just one thread, but for the however many threads we have created here. So we will also need to add, I think, we will need to change a few things. We don't want to close the thread just close the handle just now, because this, I mean, this should work. Let's leave it. The other strategy would be not to close the handle, but instead to wake all the ports up, and then close it once we know that no thread will do something with them. But for now, I think it's fine to do it in a simpler way. So we just close the port, and then we wait for the threads. So if well, we wait forever. So now if wait for multiple objects, and threads point size comma threads point data. So what this does, this is true. So what this function does is it just takes an array of objects, an array of handles to be exact, and then waits for either any of them or all of them, depending on the true parameter. If it's false, then it just waits for any of them being signaled. If it's true, then it waits until all of them are signaled, and the threads handles, the thread objects, get into a signaled state once the thread terminates. So this waits nicely. We could of course add a sort of fallback that would allow us to terminate the threads, but as I mentioned at many occasions already, terminating threads is not quite a safe thing to do, because then we are just interrupting them at whatever place, which gives you a potentially inconsistent state. As a fallback, when you are closing the application anyways, then it's fine, but if you put it into a code path which might be executed during the application's normal operation, that might then end up in a resource leak, and at some point the application will crash, so it should not be done. And since we don't know where we will use this code, we rather go with the more conservative approach. Right, the last thing to do, of course, is to close the handles to the threads. So for handle add in threads, and close thread, and just for good measure clear threads. I mean, it doesn't really matter after the destructor is done, it will be disposed of anyways, but this is a reasonably elegant approach. So right, of course we then have also we actually wanted to do this in close, not in the destructor. Zack. Okay, so this is done. Okay, so in principle our implementation here already is quite functional. It has all the needed basics. What we could do is we could try to test how well this operates when we try to compare the performance of this ALPC mechanism with, for example, just using pipes. So that might potentially be interesting, but we need to look into how easy we can implement this with our current model. The simplest approach will be that we will make the client, instead of just sending hello, send a large portion of data and then wait for a final reply, and then we will just count the time, how long it took for the final reply to arrive. So this seems like a reasonably easy approach. Another option would be to implement it such that we always send data for a constant amount of time, and then once we are done, we evaluate how much data we have successfully sent. So either option is viable. For now, let's first start to implement this in our pipe mechanism. So it will be Qt local server that we need to modify. This we want to put there, and Q local local client. Zack. So our client currently on Connect just really sends this one hello message, and this is of course quite small. So we will just switch to sending something larger. Here we are sending 10 megabytes of data, and we just send it in 100 byte large chunks. So maybe let's increase this to a kilobyte. Then we have all the data in the sending pipe, and then of course the other side, the server, will be receiving the messages on client data. We will not want to print that. We do not want to reply, and we do not want to print it. What we want to do instead is to reply just with the amount of data which we have received in total. So we are putting this in the buffer, we are clearing the buffer, so this we can also comment out for now. Instead of, we can leave the buffer, and of course we don't want the loop. Okay, let's do it differently. Let's just comment out the whole block. Can't see. And then we just always reply with a Q64 size is equals buffer punct size, right? Char, comma, caesar of. Okay. So we just reply with how many data we have already received, and then on the sender side, we should of course add some helper variable. Do we need that? Not really. So are we actually using sendbuffer for something? We are trying to use it, so let's leave this as is. We will add, although we know how much we need to receive, so we'll really just add a timer variable. 64. Let's count. And when the connection connects, then we set this to. This is not defined. Then let's go with Q date time, current date time, 2 milliseconds since epoch. This is good enough. Right, and then of course we have somewhere a receiving loop here. So again we comment this whole thing out, can't see. And in principle we just expect this to always contain, so Q set punct size is 8. So we are taking a shortcut here. Our pipe is configured such that it will deliver the messages in proper sizes. It will not break them up. So here we can just expect that we will always get the right a value back, and once we're done, of course, clear this, and in the middle, in 64, asterisk size, pass size is equals data, and then we just check. So if this is equals to what we wanted to send, this is right, so when we receive this amount of data, then we will just check how much time passed and print this to the console. Time debug sending stern per size ms that needs to be a string. Okay, yeah, let's see if this will work. So we want to create a pipe server and the pipe client, and we have a bug somewhere, call stack. Size. That is not great. Why would that fail? That's some internal problem in our Qt implementation. That's of course not great, because that's kind of outside of what we could easily fix, but we can of course hope that the reason is that we somehow use this something not quite right. But normally size of this QU in 64 charge should be right. Let's put a breakpoint here and try again. Server, client. So receive the first amount of data. Yes, I know what's wrong. I already see it. We need to take, of course, the reference of size. That's why it failed. So server, client should be doing something. Let's put a breakpoint here. Nope. Then it's hanging somewhere. Let's put a breakpoint to the other end to see that we receive even at least some data. Pipe server, client. Nope, that is we're running out of memory, so our sending is somehow bugged somewhere. We added at the beginning here this buffer mechanism. We could in principle just comment it out. Try send just comment the whole thing out, and we just go with just sending everything every time. Send buffer to send buffer size, and then we just clear it. So we can see that we ran out of memory here a couple times, close to, so at at some point we've been just sending the same data over and over again, and that has filled up some of the buffers. But it's still happening, so sorry, that's the problem. We are sending like how often we send this amount of data, so let's only go with a smaller number. It should alleviate the issue. Pod server, pod client, send complete. Let's see what crashed now. This was not right because this was sometimes, apparently here it was 0, so let's do it like this. Let's go with a for. We just process all the sent bytes, so if this is less than 8, then we continue. If it's bigger or equals 8, we keep, but we're not clear, we will remove 0, 8. Okay, let's run it again. We have read all for client, yes, server, client. Right, and now we are getting data back. So at some point we should run into this. Oh, we did already. We did already. So let's try it again, this time without breakpoints, so that we don't make it slower artificially. Server, client. Okay, that was by far not enough data because we finished in under a second. So let's maybe really go with more. I mean, that's a whole gigabyte of data that will have some effect, but if everything works, it should not. Let's just keep this on top, then we can monitor the memory usage. So we see it rising here, and then it crashes. Okay, so we cannot send that much data. Let's just, I mean, for testing, a quarter of a second is long enough that it is a valid benchmark. So let's just check if it's reproducible. Yeah, and then we will implement the same thing into our LPC port, so that we can see what's the performance of that part of our mechanism. So port client, port server. So we will need like the local client helper variable, port client, zack. Port client, local client. Let's just copy as much as we can from here. That will speed up things. Port client qt. Okay, let's just override this part, and this we just comment out. Then the replay. I also need to manipulate try send, but later this we comment out now. Okay, and then this looks correct, and then on the sender side, local server, we had this simple reply mechanism, so port server, so this we comment out, and we just reply with the size. Okay, let's see if this works. We did not forget anything. I think we did not create this, create that. and it doesn't work. So we have a problem somewhere. But it backed out. Like it connected the client, but it's not actually processing any data. We might have forgot. No, we didn't. I wanted to say we might have forgot to trigger a trigger this, not this. That, but this part was working. Client right. Let's see, client. Sorry, no. This is in on connect. This is not quite right. Let's quickly see what we did wrong here. So this is right, and here we pasted the wrong code. We wanted this data here. Send hello, and then we just overwritten the whole thing. So let's just go with this. Server client. Okay, this will take forever because we are logging so much data. You can see how long is forever, but it doesn't seem to want to finish at any point soon. So let's break it and disable all the logging. But the Visual Studio has allocated a lot of memory, as we see here, for the log lines. Now we can speed this up by terminating this thing. It's still hanging. I mean, we can also restart Visual Studio if we manage to break it. Now it's fine again. Right, so we want to remove the log lines from our implementations, those here. And in the server we also had some, so there let's disable those two. Okay, let's run it. Server, client, and it's either working or something is still okay, or data queued. So it should be now slowly receiving the data. That definitely looks like it takes too long. So something didn't quite worked out. Let's put a breakpoint here and just see whether we even received the first message properly. Although we could also put the breakpoint there. Okay. Port. Okay, so we get one message. Okay. Port socket, port client, port server. Then we are arriving at this spot. Then we try to reply. That looks correct. RPC socket. Then we go to this right with our very short reply. Zack. Prepare the header. We send the reply. That looks correct. Then of course we want on the client side to go into this read loop. 8 seems fine from the length. Let's see what the message data contains. A reasonably small number, that looks fine. This works as well. So then we should port client here. Okay, we are not triggering. Okay, we are triggering but with a delay. It seems to be working. That's very slow. Let's just run it. Now it finished. So before it somehow just maybe we missed the log line. Let's just try it again. Server, client. We might of course have some sort of timing issue again, that if you're not doing anything, we at some point run into all data queued, and that if we don't do anything, we sometimes run into a situation that something doesn't work out quite right. So this of course might happen, in which case we would need to improve here. So apparently we are kind of done, but we did not trigger this case here. So let's keep only one breakpoint and then see if we run into it. It seems like it's just very slow. Size. But in principle it's working. But it failed at some point. So what we can do to debug this is we could remember the last timestamp and then just print once per second how much data has been written already. Or we could go simply and really just for starters just print only the amount of data that was received. We see when it breaks, even if it will be much slower than normal operation. Right, that kind of looks right for now. We also might have some bug that we are just miscounting and we never trigger this case, so then we would just need to figure out where the bug is and why our counting is off by however much it is. We will once this finishes, we will see how off the counting is in fact. I think we should be done at some point. Let's see where we were. So we had decimal 150 megabyte, and we are going up to. Okay, that will take quite some time because I think we are sending. We're sending here 10. We're sending a gigabyte. That will take a long time. So now, for just to test the mechanism, we should just reduce this to just 100 megabyte by reducing this by an order of magnitude, and then we'll see what happens. Also, we might want to maybe not really buffer all the data, but instead just as a simplification only keep a count of how much we have received. But for now, let's try like this. Server, client, zack. Okay, it got stuck. it looks like it didn't send everything. It just got stuck at 37 megabyte, and before we were quite a way past that. So something might be not right with our sending code, which we have LPC socket. Let's see if we run into this bug here. I just put a breakpoint, and if we run into, then we'll see what's wrong. We kind of, I think, had quite quickly the message that everything was queued. So it really looks more like a receive side issue. Yeah, all data queued. So the sending was more or less finished instantly, just that here at some point the receiving mechanism broke. And the question is of course on which end it broke, whether it broke on the server or on the client side. Because basically both are decently possibilities. Let's just put this on the server side here. Local server Qt. On client data, and this is just adding and replying. So let's add here print out of the buffer size. This time we don't get any. Oh, I put it in the wrong place. Sorry. It was not local server, but port server here. Zack, zack. Okay, we're starting receiving. We ran into a situation where we are triggering a receive, but we do not get new data. Let's calculator decimal hex. But that looks like our 10 megabytes. So we sent everything, and then we end up in some sort of loop. Okay, what might happen is of course that we get like a lot of events being emitted, and then if the system is packed down with processing data, then it will just process some of the events, read all of the buffer that is to be read, and then we still are getting events, but nothing else is happening, in the sense that we are just not getting any more replies. This read just doesn't add new data because we already read everything. So this is probably what is happening here, but it still doesn't explain why we fail on the receiving side. So here we have our right socket. This, let's comment this out. Could also add here that if bytes available is 0, then break at 1. So if there is nothing for us to read here, we just bug out. And then we would like to see on the server side what's happening there. LPC socket write data, and this, as we said, seemed to be working correctly. We can put a breakpoint here. So m What was it? Helper. No, M should be fine. M is server side, so if this is the case, then q debug we just print out whatever it gives us, and only on the server side. So it didn't send anything. So something is broken in the reply mechanism, because here we are no longer arriving this place. Port server. Here we are also not arriving anymore, so that's interesting. Let's put a breakpoint here and rerun it once more. We should at least send one reply, I guess. Server client. Are we always running into this? That should not be. We saw before that we were reading data. Server client. Yeah. Okay. Might have the problem that our bytes available function is not working correctly. So let's remove this code for now. And then so should arrive at the server side. Socket here. Yeah, there is a small bug. We needed to dereference this. Let's run it again. So we also need to fix the bytes available function, because apparently it's not quite working right. Well, but in principle we are replying a nice amount of data, one after the other. So then we just keep replying with the same value. So it seems that the problem will be in the client's receiving mechanism. And we wanted to see this, why this is not working as well. This is for local socket. Let's put just a breakpoint here and test it where it brings us. Okay, I guess the thing is that size is always 0 and position is always 0. So we would need to override the size function of our socket. For now, let's just leave it disabled. It's something we can fix later if we want. But we want to first debug why our performance measurement doesn't work. So on this side, again, there's the client side. Client receives data, client dumps something out, and at some point it stops working. So when we uncomment this and run it again, we will see that it somehow is getting stuck at half of the data that we wanted to transfer. We could run this twice and to write down the number so that we see if it's being stuck each time exactly at the same value or just always around in the middle, which will give us an insight whether it's a very deterministic sort of bug or if we have somehow a different problem. Well, the number looks certainly somewhat random. So I would rather expect that it would be like exactly in the middle, also if it would be a non-random value. But we'll see in a second once we run this. Yeah, so it's a different number. So it's failing at some point, and then it just stays failed. So we can leave this for now. Go to our socket. Copy this, and then where is it? Read data. Our thread here. This thing will be bugging out. We could just put a breakpoint here actually to see if it's so easy to catch, and if not, then we will add some additional debugging. But it is quite likely that it might be failing here. But it didn't. It just kept running. So let's put it here so that we see whether we're actually exiting this or whether we are stuck in the receive function. Okay, it seems we are just getting stuck without the obvious reason. So we go to the client, threads, on client data, and that seems to be still doing something. And the other threads, this one, let's see, that is, well, this is just waiting on something. So let's add here a print out so that we see what we have received. Data is on the helper, this is okay. So let's go here. So if this is server, then we just message data test and we comment out the other one. This one. We need to change the focus so that our task manager is not blocking our debug database. Okay, server, client. Okay, there we have something screwed up. This didn't print correctly. Message receive buffer append message data. Okay, that is weird. That should be working. Let's put a breakpoint and see why this is wrong. So length is servers. Wait. We want this, of course, on the client side. So now we need to negate this. Okay. Data contains. Yeah, that's fine. Okay, so now we have the client's receive and data processing part. We'll see how far we go. It might be that in the end it's something in the Qt event handling. If we are emitting too many events, we might want to change our mechanism such that we receive some amount of data, group them together, and then receive a notification on a timer or something of this sort. So there are various ways how things can be improved on our implementation. Our implementation is just a very, very basic one, so to say. But that seems to be the case. I'm cautiously optimistic that we'll count to the whole however many 100 MB I think we are testing. The other mechanism didn't go so far on its own. It's admittedly quite slow, but this is more about our implementation than about the underlying mechanism. So if we improve on this, it should behave much better once we iron out all the issues, although we might not have enough time to fix everything. But only fixing the most important things is, I think, good enough. Okay, so this is the value we arrive at the end, which I think is the, yeah. So we are receiving all the replies, but what is then somehow happening is that the user part of the thing here, we see that the thing is stuck in some on client. It's actually stuck in one of our functions, port client. Oh, I see why. This is a mistake. This should be break. Should be a break. So we had implemented a bug there, which just made it hang. So if we now, actually now I would be quite confident that this might work out fine. Let's just run it again. Right, and we of course need to change the focus here. Just press F5 until it can write to the file again. Client, server client. Yeah, it works. It's slower, obviously, a bit than what we could do before, but it's not that much slower than the highly optimized pipe mechanism. So we can take a look how this would behave if we would change the port message size. Was it I think the real limit is like 6 something, but I don't remember. Let's just see if it works like this. If we set it too much, then it will just bug out in port creation. Yeah, so obviously increasing the message size improves performance quite a bit. We cannot really increase it more. I think if we go even further, then it will just bug out and not create the port anymore. For this, we would need to switch to ALPC. Yeah, it's just bugging out and not connecting. Which we could, in principle, of course, do if we would add quite a lot of more code, but we don't really have time for this today. And well, since we have a working and somewhat okay-ish performing code here, I think this is a good place to stop our implementation. If are there any questions? Okay, does not seem like they are. So if there are no questions, then I would say we will finish this lecture a bit early today. Usually we are a bit over time. This time we'll be a bit under time. I don't think that there is a point in starting some other project now in the last half an hour. Ideally, you should submit your final project until the 28th of the next week. Or was it the 5th of the over next week? I don't remember what I said in the Moodle. Both dates would be fine. Let's just say you have time until the 5th of the. I will quickly check this in the Moodle, then we will know exactly what I said, so that we don't introduce any unclarities. Comac final project. Settings. Okay, so it is said in the module that it should be finished on the 29th of this month, so today, next week, and you should try to stick to it, to this. If you have any questions, you can call me. Sorry, you can email me. You can email me at any time. My email address you should have from the lecture index. If you need more time, then let me know up front. Then I will just wait for your submission. Yeah, and since this is this, then have a nice semester break and good luck with your other exams. And I think some of you did not participate in the part 1 in the last semester, so if you want, you can of course participate in the part 1 next semester. It is touching quite a bit different topics, so there we have just C++, not using any Qts, and on a much lower level, so it might also be interesting to you. So I guess that's it. Bye bye.